Quantitative analysis is not something you choose at the end of a dissertation. By the time you arrive at this stage, every major decision has already been made for you. Your research problem has identified a measurable tension. Your literature gap has shown what pattern, relationship, or difference is not yet understood. Your methodology has confirmed that numerical evidence is required. Your design has shaped the kind of quantitative knowledge you intend to produce. Your purpose statement has pointed toward the analytical direction of the study. Your research questions and hypotheses have told the reader exactly what will be tested. When all of these pieces are aligned, the statistical analysis is no longer a personal preference. It is the only logical outcome of the study you have already designed. The most important signal for selecting a statistical test is the verb used in your research question. The verb tells the reader what kind of answer you are seeking, and each verb belongs to a specific family of statistical tests. When your question uses the word relationship, you are asking how two measured variables move together, and in what direction. A relationship means that as one variable increases or decreases, the other tends to increase, decrease, or remain unrelated. It does not mean that one variable causes the other. This verb signals correlation. When your question uses the word predict, you are asking whether one or more variables can be used to estimate or explain variation in an outcome. This signals regression. When your question uses the word association, you are asking whether two categories are connected in a way that is unlikely to be random. This signals chi-square. When your question uses the phrase statistically significant difference, you are asking whether groups differ in their average scores, which signals group comparison tests such as t-tests, ANOVA, ANCOVA, or MANCOVA. The verb must appear in the question itself because it establishes the statistical logic of the study. To see how this alignment works from start to finish, consider a simple example. Imagine a study asking, what is the relationship between teacher self-efficacy scores and student engagement scores? The verb is relationship. Both variables are measured using validated scales that produce numeric scores. The outcome is continuous, the predictor is continuous, and the goal is to see how the two move together. Because of this alignment, correlation is the only appropriate analysis. No other test answers that question as written. The verb alone is not enough. The data produced by your variables must also match the test. This is where understanding variable types becomes essential. Categorical variables place participants into groups such as instructional modality, program type, or completion status. These variables describe kind, not amount. Ordinal variables show order, but not equal spacing, such as a single Likert scale item ranging from strongly disagree to strongly agree. Continuous variables represent measured amounts with meaningful intervals, such as test scores, percentages, time, frequency, or composite scale scores created by combining multiple Likert items into a validated instrument score. A single Likert item is not continuous and cannot support parametric tests on its own. When multiple Likert items are combined into a scale score, the result behaves as continuous data and can be analyzed using correlation, regression, or group comparison tests. Assigning numbers to categories does not change the nature of the variable. The type of measurement determines what analysis is possible, not the numbers visible in the dataset. Understanding how predictors and outcomes pair together makes test selection much clearer. When both the predictor and the outcome are continuous and the question asks about relationship, correlation is required. When both variables are continuous and the question asks about prediction, regression is required. Correlation always involves exactly two continuous variables and only describes how they move together, while regression models prediction and can include one predictor or many. When the outcome is categorical and the question asks about prediction, logistic regression is required instead of linear regression. Logistic regression predicts the odds of belonging to a category rather than estimating a numeric score, which is why it is commonly used for outcomes such as retention, completion, passing, or participation. Logistic regression is still part of the regression family and aligns with the verb predict, but it requires a categorical outcome and sufficient cases in each category. when both the predictor and the outcome are categorical and the question asks about association. Chi-square is the aligned analysis. Association in this context does not mean how variables move together numerically. It means whether the pattern of observed counts across categories differs from what would be expected by chance. Chi-square works with frequencies, not scores. Each participant contributes one observation to a category combination. For example, a study might ask whether there is an association between instructional modality and course completion status. Each student is counted once based on whether they were in an online or face-to-face course, and whether they completed or did not complete the course. The analysis compares how many students fall into each category combination, and determines whether the pattern is unlikely to have occurred by chance. When the outcome is continuous and the predictor is categorical, group comparison tests are required. Two independent groups require an independent samples t-test. Two related measurements from the same participants, such as pre- and post-intervention scores, require a paired samples t-test. Three or more independent groups require ANOVA. Running multiple t-tests instead of ANOVA is not acceptable because it increases the risk of false findings. Some studies include covariates, which must be understood conceptually. A covariate is a continuous variable that influences the outcome and is included to make group comparisons more precise. It is not the focus of the research question and does not replace the independent variable. Instead, it accounts for background variation that might otherwise distort group differences. For example, when comparing student achievement across instructional models, prior achievement is often included as a covariate. Including this covariate allows the analysis to compare groups as if they began at similar starting points. When a covariate is included, ANOVA becomes ANCOVA. When multiple continuous outcomes are analyzed together and covariates are present, the analysis becomes MANCOVA. Multiple outcomes means more than one dependent variable, not more predictors. Sample size and statistical power are central to analysis alignment. Statistical power refers to a study's ability to detect a real effect when one exists. A study with low power may fail to find statistical significance even when meaningful differences or relationships are present. Power depends on sample size, the strength of the effect, and the type of test used. Correlation and regression require larger samples to produce stable estimates. Logistic regression requires enough cases in each category to model odds reliably. Chi-square requires sufficient observations in each cell of the contingency table. ANOVA and ANCOVA require adequate group sizes, and MANCOVA requires the largest samples because it analyzes multiple outcomes simultaneously. Even a perfectly aligned test cannot produce defensible results if the data are insufficient. All of the analyses discussed here are parametric tests, meaning they rely on assumptions about the data. These include normally distributed outcomes, similar variability across groups, linear relationships between continuous variables, and independence of observations. If these assumptions are violated, parametric tests may no longer be appropriate. Ordinal data, severely skewed distributions, or very small samples may require non-parametric alternatives, which will be addressed separately. Statistical significance alone is not enough. Alongside significance, researchers must consider effect size, which describes how large or meaningful a relationship or difference actually is. A result can be statistically significant, but practically small. Effect size helps researchers interpret findings responsibly and communicate their importance accurately. There are several common pitfalls that undermine quantitative studies. Correlation does not imply causation. Regression prediction does not prove cause and effect. Chi-square cannot be used with continuous variables. Single Likert items cannot be analyzed with parametric tests. ANOVA only indicates that a difference exists. Post hoc tests are required to identify which groups differ. Logistic regression models odds, not means. Coding categories with numbers does not change the nature of the variable. Statistical software will run any test you request, but it will not determine whether the test is appropriate. Alignment is the responsibility of the researcher. When all pieces of the study are aligned, analysis becomes clear. The research problem identifies a measurable issue. The gap clarifies what pattern or difference is missing. The methodology establishes the need for numerical evidence. The design determines the analytical pathway. The research question verb signals the test family. The variables determine the data type. The sample determines feasibility and power. Each research question aligns to one analysis. When these elements work together, the correct statistical test is no longer confusing. Quantitative analysis is not about choosing a technique. It is about honoring the logic of the study you have already built.